Have you ever used a chatbot and just had to stop and wonder, how does this even work? How can a pile of code create text that feels so coherent, so creative, sometimes so startlingly human? Well, today, we're going to pull back the curtain and look at the hidden geometry that makes these large language models actually tick. And yeah, this quote, it just nails the feeling, doesn't it? That sense of disbelief. It feels like a magic trick. But it's not magic. It's a combination of really clever architecture and just mind-boggling scale. And the craziest part is, even when you know how the trick is done, it is still wildly impressive. And this right here shows you the incredible leap we're talking about. On the left, you've got an older, smaller model, GPT-2. You give it a prompt, and the story it spits out kind of falls apart pretty quickly. But then you look at its much bigger successor, GPT-3. Same process, but whoa. Suddenly, you get a story that actually hangs together. So what changed? How does just making it bigger suddenly create this magic? The answer, and this might surprise you, is that this entire incredibly complex system is built on one very, very simple task: predicting the next word. That's the whole game. It's not trying to understand anything the way we do. It's just playing an unbelievably sophisticated game of what comes next. That's it. That is the core loop. You know when you see a chatbot typing out its response one word at a time? This is literally what's happening under the hood. It predicts the most likely next word, tacks it onto the end of the sentence, and then uses that brand new, slightly longer sentence to predict the next word over and over and over. The entire conversation is just one long chain reaction of these predictions. Okay, but if it's just predicting the next word, how is it so good at it? I mean, really good. To get that, we have to pop the hood and look inside the engine. We need to peek inside the black box of the architecture known as a transformer. So let's follow your words as they go on a little journey through the model. So here's the roadmap, the 5 main steps. First, your text gets chopped up into pieces called tokens. Then each of those tokens gets turned into a long list of numbers, a vector. And the second step, embedding, this is where the magic really starts. It's where the geometry comes in. After that, all the vectors talk to each other to figure out the context. Then they're turned back into word scores. And finally, those scores are used to make the prediction. We're going to really zoom in on step 2, embedding, because that is the foundation for everything else. All right, let's get into what is, for my money, the absolute coolest part of this whole thing. This is the moment where language stops being just words on a screen and becomes actual geometry, points on a map. This is a word embedding. The best way to picture it is like a giant invisible map. Every single word or piece of a word the AI knows has its own unique address on this map. And that address isn't random, it's a set of coordinates. And its location on the map is all about its meaning. And when I say this map is giant, I am not kidding. For a model like GPT-3, we're not talking about a 2D map or a 3D map. We are talking about a map with over 12,000 dimensions. Just try to wrap your head around that. It's a space so complex we literally cannot visualize it. But for the AI, this is the world where language lives. Now here is the absolute genius of it all. The way the words are arranged on this map is not random. The model learns to organize them so that directions on the map actually mean something. So for instance, the direction you travel to get from the word man to the word woman, that direction literally represents the concept of gender. Or the path from France to Paris could represent the whole idea of a capital city. And this leads to some wild possibilities. It means we can do math with concepts, literally. So check this out. What happens if we take the location of king and we subtract the direction for man and then we add the direction for woman? What do you think we'd end up with? I mean, really think about that. We're doing vector math with ideas. What word do you think is sitting at the destination point of that calculation? The resulting vector lands almost exactly on top of the vector for queen. And here is the mind-blowing part. Nobody ever explicitly taught the model that rule. It figured out this entire geometric relationship all on its own, just by reading a huge chunk of the internet. So how does the model actually measure these relationships? It uses a handy mathematical tool called the dot product. You don't need to know the formula. Just think of it like a similarity detector. If two vectors are pointing in a similar direction, they get a high dot product score. If they're totally unrelated, the score is near 0. Simple as that.
So let's make that more concrete. Say we create a vector for the idea of plurality by just taking the vector for cats and subtracting the vector for cat. Now we have a direction that means plural. We can test how much other words align with it. And look at the scores. The dot product for cats is way higher than for cat. Same for dogs versus dog. The math is actually measuring how plural a word is. Okay, so let's recap. We have this incredible geometric map of language, and we have a tool, the dot product, to measure the relationships within it. So now let's bring it all back home. How does this help us predict the next word? So after your prompt has traveled through the model and all the vectors have soaked up the necessary context, the model looks at the very last one. This final vector holds all the meaning of what came before. It then uses a giant lookup table, called the unembedding matrix, to translate that vector back into a score for every single word it knows. These raw scores, or logits, are like the model's first guess for how good a fit each word is. But those raw scores are pretty messy. What we really want are clean probabilities. And that's where the softmax function comes in. It's a clever process that takes that long list of logits and kind of squishes and stretches them until they all fit neatly between 0 and 1, and the whole list adds up to 100%. So now we have a clean probability for every possible next word.
And here's where we get some creative control. There's a setting you can adjust called temperature. Think of it as a creativity dial. If you turn the temperature down low, the model will almost always pick the most obvious, highest probability word. The result is pretty predictable, maybe a little boring. But if you crank the temperature up, you give the weirder, less likely words a fighting chance. This can lead to more original text, but turn it up too high and it just starts spouting nonsense.
So, we've seen all the mechanics, the geometric embeddings, the context, the probability distributions, but that still doesn't fully answer the question, how does all this math feel like understanding? Well, the secret ingredient is just one word: scale. Take a look at that number, 175 billion. That's how many parameters, or think of them as tiny tunable knobs and dials, are inside GPT-3. Every single one of them helps to define and shape that vast geometric space of meaning. And this is a really crucial distinction to make. There are two types of numbers flowing through the system. You have the model weights, those 175 billion parameters. That's the permanent brain of the AI, the knowledge it learned during training. And then you have the vectors from your prompt. Those are temporary. They're like a thought just passing through that fixed brain. Those 175 billion weights are what hold everything the model knows. And that right there is the key takeaway. When you combine this geometric way of representing language with a system that has 175 billion dials to fine-tune all those relationships, you get something that can navigate that space of meaning with incredible nuance. And because it's so good at navigating that space, it gets really, really good at predicting the next word. So good that it starts to feel like intuition. It starts to feel human. Which leaves us with one final big question to chew on. Is this hidden geometry a genuinely new kind of thought? A new form of intelligence? Or is it just an incredibly complex mirror reflecting back at us the patterns and structures already hidden in the billions of words that we, humans, have written? Is it thinking, or is it the ultimate echo? Something to ponder next time you chat with an AI.